It's a great pleasure to introduce Jan LeCun. Jan's a professor in the Courant Institute at NYU, which is the joint math and computer science department there. Jan's done a lot of great work in learning and vision. He did his PhD in France and then was in Jeff Hinton's group in Toronto, and then went to AT&T, where he was for a number of years. He ran a department there which did a lot of very practical computer vision, including some OCR and check reading and the Deja Vu document compression system, which a lot of you have probably used. Jan's a great proponent of kind of not forgetting what all got us interested in AI in the beginning and thinking about kind of hard vision problems and how we can really build representations that scale up to really recognizing objects and stuff like that. So I think that's a great motivation to keep us all on track. Jan is someone who was almost involved with Google at various points in the past, but it never quite happened. But it's great to have him visit. So he told me a great story yesterday, which is that he, accidentally forgot to answer an email from Larry Page in 2001, which I think is a distinction that falls to very few people these days. So anyway, today he's going to talk to us about visual perception with deep learning.
Thank you, Sam. All right, so it's a real pleasure to be here. Last time I was here was, I guess, in early 2002. The place was very different back then. But some of the same people are here. I can recognize. Peter was here. OK, so I'm going to talk about computer vision, machine learning, and sort of a bit on a large scale, and also on about robotics to some extent. And so one of the problems I've been sort of obsessed with for quite a long time is sort of how do we learn representations. So I'm not necessarily particularly interested in vision per se. I'm interested in sort of complicated learning. And the reason why I'm sort of doing vision and robotics is because I think it's one of the most challenging problems for learning. So if we can solve computer vision with machine learning, I think we can pretty much solve everything. Maybe not language. Maybe Fernando will disagree with that. But I think it's sort of very challenging because it's very high-dimensional, very sort of complicated. So what tells you that this little airplane is the same whatever viewpoint you're looking at it from, what background it's in front of, what lighting condition, the appearance of it will change a lot. And what a good learning system should do is sort of develop internal representations for those objects that are invariant to those transformations, possible transformation of these objects, and somehow learn it by itself. And the brain does it pretty well, and there's considerable evidence that it's actually learned. It's not sort of built by genetics or anything. And we ought to be able to reproduce this in computers, and so far we really haven't been able to do it, to do a good job at it. Certainly not with learning. So one question is, how do we learn from just a few examples, and just seeing a few examples of objects? So you can probably readily identify those flying contraptions as flying contraptions, but it's kind of likely that many of you haven't never seen those particular airplanes before, or I don't know if you could call them airplanes actually, but so somehow you've sort of developed some representation of flying contraptions that sort of match these particular objects. So there's evidence that human recognition is a very, very fast process. People have sort of measured, how long it takes for the signal to go from the retina to the infratemporal cortex, which is where objects are encoded, and it's less than 100 milliseconds. So there's basically no time for a very sort of complicated process to take place. It's essentially a feed-forward process, at least for sort of recognizing everyday objects, not for sort of complex, certain complex visual tasks, but for sort of recognizing, a chair, a car, things that have a short word. It goes extremely quickly. What anatomy tells us is that the visual cortex, until sort of this IT area, is composed of roughly 10 layers of stuff, neurons. Okay. So think about a neural network with about 10 layers. Now, we don't have any learning algorithms that can train a neural network with 10 layers with sort of traditional learning algorithms. And so one of the things I'm going to try to tell you about is sort of new sort of categories of learning algorithms that, to some extent, can address that problem. Okay, so here's the sort of traditional way of doing computer vision. You start with an image, you build by hand with years of experience some sort of way of pre-processing this image in a representation that takes care of eliminating the irrelevant variabilities of this object due to, say, illuminations and things like this. And then you plug your favorite trainable classifier on top of it and hope for the best. And this is, it's a method that works pretty well in a lot of instances, but is not going to explain how, we solve every learning problem that we're facing with. So one problem in particular is that for every new task that you want to solve, you have to rebuild this preprocessor essentially by hand. And that's not a nice thing to do. I kind of call this sort of the shadow architecture. Shadow in the sense that it's got, sort of a more or less fixed preprocessing, and then some sort of, adaptable layer on top, which is very simple, but sort of takes care of classification. So an example of this is the popular kernel methods, which essentially work by, you build a kernel function, which essentially sort of is a matching function that sort of measures the similarity or dissimilarity between your current inputs and all the samples you have in your training set. And then you take those matching scores, compute a weighted sum of those scores, and that's the decision. Okay, so the only learning takes place in those coefficients. That's where those coefficients are subject to learning. They can adapt, but that's the only place where learning takes place. And so essentially, it's glorified template matching. If the kernel function is something that measures similarity, that's just glorified template matching. It's kind of a little notch above nearest neighbor classification. If the kernel is very simple, then it's like linear classifier, which is nothing we didn't know about before. So there's no way we're going to solve sort of complex AI problems like natural language, computer vision, speech with this kind of model. It's just not going to work. It's like climbing a ladder to sort of try to reach the moon. It's just not going to work. At least not with learning. It might work by building it by hand, and there's big success in this. But I'm not saying that there is no success in sort of engineering approaches to this, but it's not how we're going to build sort of a learning machine that solves a lot of problems. So the alternative to this is something that some of us for the last few years have come to call deep learning. And it's the idea that you can sort of stack multiple modules, each of which is a trainable module. And by sort of having multiple layers of those, each of which can implement complex nonlinear functions, you can sort of go from sort of low-level representations to sort of higher-level internal representations that maybe can capture those variations I was talking about. So perhaps as you go up the layers, you might be able to build representations in which a view of this object under any kind of viewpoint is essentially the same. The representation is invariant to those transformations. But of course, how are we going to do this? So the first thing you can ask, from a theoretical point of view, is why would we need deep architectures? The theory tells us that with the kernel methods I was telling you about before, you can approximate any function you want. So why would you need anything else? And of course, the answer to this is a problem of efficiency. You cannot represent. There are a lot of functions you cannot represent efficiently with just a kernel type representation. You need essentially a very, very large number of templates with which to match your input vectors to do a good job. So for example, if you want to recognize this with template matching, you need a view of this object like this, like this, like this, like this, like that. And if you want to recognize other types of planes, you need templates for those other types of airplanes. If you want different backgrounds, you need templates for different backgrounds, different illuminations. And pretty soon, it explodes in a sort of exponential way. There's no way you can solve that problem. And that's the problem every computer vision person knows about that you have to get around. So there is some theoretical evidence, which I'm not going to get into, that if you have multiple layers, you can sort of more efficiently represent certain types of complex functions. For those of you in the audience who sort of have an engineering background, if you want to design a circuit, say a Boolean circuit for a Boolean function, you can always represent it as a conjunctive normal form or disjunctive normal form. That's basically a two-layer implementation of that function, right? Any function can be implemented with two layers. But it might require an exponential number of minterms. Whereas if you allow yourself to have multiple logic layers, then it might end up being a lot smaller. So you want to implement a 32-bit by 32-bit multiplier, you're not going to do it with a two-layer DNF. It's going to be very large. Okay, so you're going to do it with addition and carry propagation and things like that, which takes more layers. So there are functions that are more efficiently represented with more layers, and what is true for logic circuits is also true for recognition functions. So basically, a deep architecture trades space for time. That's essentially what it does. This is kind of a joke that I kind of borrowed from Jeff Hinton, who I think gave a talk here a few months ago, which is that there's sort of several attitudes you can have to approach the problem of sort of building artificially intelligent machines. The first one is defeatism. Since there is no good sort of parameterization of the set of functions that would sort of implement artificially intelligent tasks, let's just parameterize a much smaller set for each specific task through careful engineering. That's the approach that most people have adopted for the last 50 years. There's denial. Kernel machines can approximate anything we want, and the learning theory tells us that we can learn anything with this. Why would we need anything else? But I kind of said a few things against this argument before. And the third one is optimism, which I'm sort of placing myself squarely into, just because.
I don't understand your denial point. Either you can approximate universally or you cannot.
You can, but not efficiently. You can approximate, but just not efficiently. Okay? So it's this exponential number of templates problem. You can do it, but it's just exponential. Okay, so let's see how far we can go with deep learning in a kind of supervised way. And this is some relatively old work that I've done, but that some of you have seen. But I want to show it here. So there are a few situations where you can use sort of traditional supervised learning algorithm like backpropagation, which is sort of the traditional learning algorithm for neural nets, to train deep architectures up to something like six or seven layers. And it's if you build a particular structure into the network. Okay, so let's say you want to do face detection, object recognition, robotic vision, something like that. You know that there is very strong correlation between neighboring pixels and images, and so you can sort of get inspiration from the visual cortex and say, I want to combine, I want to detect local features because local features are kind of a good way of representing objects. So people have had this idea for a long time, neuroscientists in the 60s, some people in sort of computational neuroscience since the 70s, and I've been working on this since the 80s. And the idea is basically to build a neural network in such a way that each unit in a particular layer only looks at a local neighborhood in the previous layer, and you can build some sort of shift invariance in that thing. So rather than going into the details of this, let me show you an example. So here's an example of such a network. Here is an input retina, if you will, where each pixel is kind of, represents sort of a grayscale or something. And this is the first layer. The first layer is composed of multiple planes, and which we call feature maps. And each feature map, each pixel here is the result of a linear combination of a local patch in the previous in the input, which is repeated over the entire field. So essentially, you can view the result. You can view one of those planes as the result of applying a convolutional filter to the entire input, and then passing the result through a sigmoid nonlinearity. So it's like it's like a filter you apply to the entire image, and you pass it through a nonlinearity. But the coefficients in that filters, in those filters, are going to be learned, right? So each of those planes is the output of a different filter, the coefficients of which are learned, supervised. And as we go up the layer, we repeat essentially the same operation, but we reduce the resolution every time. The reason for reducing the resolution is to kind of build a little bit of shift invariance in it, okay? Or distortion invariance. So if I shift the image on the input, as you go up the layers, the shift is not as big because the resolution is lower, and so the representation doesn't change as much, and so it's easier to take care of those variations with respect to shift, rotation, scale, etc. So people sort of build systems like this with, sort of simulated them since the 70s, Fukushima with the neocognitron, so I've been working on this since the 80s. Tony Poggio has a similar model he calls HMAX, which he's been working on the last few years as kind of a model of the visual cortex. Shimon Ullman has kind of similar models, but not sort of very different learning algorithms. Poggio also used completely different learning algorithms. David Lowe also has been working on similar models inspired by Poggio. And with this, we can do all kinds of cool things like object recognition, face detection. So let me show you a demo of this, actually, just for face detection. So let's see. not this one. OK, so this is a convolutional net phase detector. So I'm holding this little webcam here, which I'm pointing at myself. So I've not used myself to train the system. So unfortunately, I don't know if I can point it at Fernando because it's a little too far. He might be a little too small here in the picture. Yeah, it's not going to see you because you're too far. You know, we can detect sort of any number of faces essentially in real time. This is not a particularly efficient implementation either. So I'm going to make Peter happy. This is actually implemented in Lisp. Oops, and he went back to the first slide. OK, so if we compare sort of those kind of deep architectures with sort of 6, 7 layers or so with sort of shallow one like super vector machines on visual tasks, it works much, much better. It's faster, it learns faster, it's got better accuracy. So on things like MNIST, which is a handwriting recognition task, we can get down to about 0.4% with this, whereas SVMs have a hard time going below sort of 0.7, roughly, and are much, much, much slower. For object recognition, the difference is even larger. I'll show you a demo of this in a minute. So here is a task for object recognition. So we have 5 categories: animals, humans, airplanes, trucks, and cars. And for each category, we have 10 objects. We're going to use 5 objects for training and 5 objects for test. And for each object, we have lots of different views of those objects under different illuminations, different viewpoints. So if you use images like this with sort of different illuminations and viewpoints, you train on those, test on those, you get on the order of 6% error with those convolutional nets, and on the order of 11% error or so with things like super vector machines in the sort of the best instance. This is from raw pixels. Of course, you can always extract features and do a better job, but this is sort of to test learning algorithms. It's not kind of to test vision. If you go to sort of slightly more complex images, so the same kind of objects, but placed on sort of very complex backgrounds, the difference is even more striking. So a super vector machine really doesn't do a good job on this. It's sort of, the algorithms basically break down. You get something like 43% error, which is horrible. With a convolutional net, you can get down to about 8%, and with a few tricks, you can get down to about 6%. And this runs in real time, too. And the learning also is much faster with those convolutional nets than what you can get with SVM. So let me show you a demo of this again. OK, so I haven't tested this here, so I'm sort of going on a limb here. OK, so I'm holding this webcam again. Here is this little airplane. Put it on the ground. And this is an airplane. Let me try out something else. Perhaps I have this little G.I. Joe guy. That's a human, and that's an airplane. Let me see if I have something else. Maybe that's a truck. It's a truck without the wheels. Well, it says an animal. OK, so that's the demo syndrome. OK, so you see, so we can do a decent job at sort of real-time object recognition. It's independent of viewpoints, hopefully. Independent of lighting condition, relatively independent of background, although it doesn't do such a good job on background. It's really not an object detector. It's more of an object recognizer. So it wants to classify any object it sees as one of those 5 categories. So if I point it at the crowd here, it's going to find all kinds of weird objects in it. OK? Because it's really not been trained to kind of reject things as anything else than what it's been trained on. OK, so this is not the ultimate answer to computer vision, right? It's not. But it does sort of, viewpoint invariant, lighting invariant, to some extent background invariant object recognition. It can deal with small occlusions as well. OK, so what we've established is that we can do a relatively good job at sort of classifying objects if we have enough training sample. Oh, let me show another one. So this is another application of supervised convolutional nets that we apply to driving robots. So we basically build this little robot guy out of radio-controlled truck parts and have it driven by someone using remote control. And the person was instructed to basically drive straight until an obstacle would be roughly 1.5 meters or 2 meters away, and then veer off, okay? And so we recorded the video together with the steering angles, and then trained one of those convolutional nets to basically map the videos from a single frame pair from the two cameras to the steering angle provided by the human. And after the system is trained, we just let it loose and let it run by itself. And I've got a couple of videos of that. So this is what the robot looks like when it drives itself around in this sort of busy backyard here. Question?
Did you make any effort to try to train it on mild?
Yeah, it works slightly worse, but not hugely worse. And so this is sort of from the viewpoint of the robot. So here it's kind of seeing this car veering off to the right. I think this backhoe or whatever, veering up to the left a little bit, and sort of negotiating its way through this little narrow passage here. So it's completely reactive. There is no planning. There's no, there's no tricks. Basically, we feed the raw video frames to the convolutional net and just let it loose. It works pretty well. Okay, so this is what we can do with kind of supervised learning with deep architectures, with essentially zero preprocessing, just raw pixels, okay? And I know some people in the room have been playing with this for other applications. Okay, the main problem with this is that it needs a huge amount of training samples. So we built handwriting recognition systems with this that required hundreds of thousands of samples. Face detection needs something like 50,000 samples. The robot is 20 minutes of driving, so it's several tens of thousands of frames. The object recognition is something like 300,000 images, individual images. So it's it's painful. So we can't use this to let a robot loose and expect it to kind of learn the task by itself. It would require too many labeled samples. So what we need is something like more akin to sort of biological learning, which would be sort of unsupervised. So if we had a machine that could sort of learn the features by itself and then require only sort of a few samples to sort of map those features or invariant representations to categories with a very simple classifier, that would be ideal. And that's basically the idea behind this sort of deep learning, sort of renewal of interest behind those sort of deep learning methods. Okay? So this is sort of the more technical part of the talk right now. So the basic idea of deep architectures is the following, or the way I view it is the following. Basically, we're going to build a sort of a hierarchy of modules. Okay, so each of those modules is kind of a layer or a stage in the architecture, and each of those modules takes two inputs. So it's got really no real output to speak of. It takes two inputs, one of which is going to be the actual input, things from the camera, let's say, and the other one is going to be feature representations of those things. And the output is a single number, which you can interpret as a log likelihood or an energy, which is going to measure how well those two things match. Okay? So if you put the image of a truck and the sort of feature vector for a truck, those things will tell you happy, and if those two things don't match, it'll tell you unhappy. Okay? And we're going to stack multiple layers of those, and the input of one stage is going to be the output of the previous stage. So basically, if we find a feature here that sort of matches that, we're going to use that as the input to the next layer, and he's going to find a feature that matches its own input. Okay? So the way we operate the machine is that we put an input, and then we search over feature vectors here for the one that minimizes this, this output, a negative log likelihood or an energy. Okay? Once we're happy with this one, we now search for the value of this guy that minimizes this output, and then we keep going. Okay? And the way we're going to train this is with some criterion that I'm going to talk about in a minute. So each of those boxes is going to have trainable parameters, which I denote by W. Okay, so let's focus on one of those modules. So you can view this in sort of probabilistic framework as a module like this giving you sort of a probability over y, or a density function, a probabilistic density function over y, given the parameters inside of that box, as e to the minus some constant, the energy of that box, divided by the sum over all possible y of the energy. Okay, so it's a traditional way of turning energy functions, any energy function, into a probability distribution using a Gibbs distribution. And this energy we're going to define as the minimum over z of an energy function that takes all of those three variables into account. Okay. All those two variables into account, y and z, okay? So we have E of y, z, and w, and E of y and w is just the minimum over z of E and E of y, z, and w. All right? So again, the process is we plug a y, find for the z that minimizes the output, and that's E of y, that's E of y w, and if we want a probability density, that's what we do. So this is like a maximum posteriori inference estimation of z using a density model. Okay, so how are we going to train this? The way we're going to train this in sort of this probabilistic framework, we're going to give high probabilities to things we observe and low probabilities to things we don't observe. Or in energy terms, we're going to give low probabilities to things we observe, like this and that, and high probability to everything else. Okay? Shape the energy surface in the right place, in the right way. Okay, so the traditional way of doing this is using sort of a probabilistic approach. You say, I want to maximize the likelihood of the data under the model. Okay, so P of y, w. So basically, when you observe a sample, you say, I want to make the probability of that sample as high under the model, and I want to make the probability of everything else low. And the fact that the probability of everything else is going to be made low is because of this denominator term, which forces the sum of the probabilities to be 1, essentially. All right? So take minus log of this, so you have a nice function to minimize. That's negative low likelihood loss. So this is the energy of a training sample, and this is the sum of, I forgot a log here. There's a log here. This is the sum. This is a log of the sum of the exponential of the energies of everything else. Okay, imagine there is a log. So you can do this with gradient descent, okay? And gradient descent will say, change the parameter vector in such a way that the increment with which you're going to change the parameter vector is going to be the derivative of the energy with respect to the parameter vector at the training sample. Okay, and then you have this horrible contrastive term, which is the integral over all possible input vectors of the derivative of the energy with respect to the parameter vector weighted by the probability under the model of that particular input vector. Okay, and this thing you can't compute because it's a sum over all possible inputs. If you have a high-dimensional input, it's horrible. You can't compute this, okay? So basically what this will do is that it will push down on the energy of the of the current training sample and push up on the energy of everything else. And the problem is that making the energy of everything else large is horribly complicated because there's just too many everything else's. So that's what we call the normalization problem that the machine learning community has been struggling with for years. But if we had a model like this, it would be really cool. We could do all kinds of different things, like say denoising. If you have a good model of sort of probabilistic model of the world, we could predict everything that happens in the world. If we had, say, a model over images, which would, of course, be high-dimensional of this, we could say, here is, clean images would have low energy, and noisy images would have high energy. So if we have a noisy image, we look for the lowest, the low energy image that's nearby, and we basically cleaned up the image. Okay, so there is a trick that Jeff Hinton came up with a while back called contrasted divergence, and the idea is not to pull up on the energy of everything else, but only pull up on the energies of nearby points to the training samples that happen to have low energy, okay? So what you really want is, if the energy has that shape, as I show here, and your training sample is here under this, this green arrow, you want to make the energy of this low, and you want the energy of that guy high because that happens to be not a training sample that has low energy. It should have a higher energy, right? So push up on this guy and sort of reshape your energy surface that way. If you do this enough times, the energy surface is going to take the right shape and eventually have minima, local minima around training samples. So this is nice and cool, and I'm sure Jeff talked about this when he came here. And there's lots of things where it works really well. But it's got a problem, which is that in high dimensions, it doesn't work so well. The problem is that there's just too many places to have to push up, whose energy you have to pull up. Dimension is just too high. So if your energy surface is very flexible, pushing up on all the areas that need to be pushed up is just hopeless. You sort of never can get it to adopt the right shape. So you need some sort of more wholesale way of pushing up the energy of things you don't observe. And there's a way to do this for a particular type of architecture that I call the encoder-decoder architecture. Okay? So remember the modules that we're going to stack? We're going to build this. We're going to build them in the following way. We're going to build them in the way where we start with an input, run the input through an encoder, some sort of parameterized function we're going to learn. We're going to get a feature vector here. We're going to run that through a decoder and reconstruct the input from that decoder. And what we're going to train this thing to do is basically minimize the reconstruction error under some constraints on the code. And with the right setting, we don't have to pull up on the energy of anything. Okay? And so if we are happy with this, we can kind of stack multiple layers of those to kind of build those sort of deep learning architectures. Okay, so in fact, the architecture we're going to use is something a little more general than this. It's something like that, where here is the input. We run the input through the encoder. And the code here is, again, an input. It's not an output to anything. It's an input to every module it sees. You see the arrows go into all the modules. Okay? So what we're going to do is we're going to search for the value of this that minimizes the overall energy. And the overall energy of that module is the sum of three terms. It's the sum of the reconstruction energy. So it's the difference between what the model reconstructs from the code and the original input, plus another term which is kind of a prediction energy. So this energy is the difference between the code that we get here and what the encoder predicted the code should be. And the third term is something we call a sparsity term. It's a constraint on the code to make sure that it doesn't have too much information in it. And I'm going to say in a minute why we need that. So basically, the way we operate this is plug an input here, look for the value of this that minimizes the sum of those three terms. Okay? And once you have that, tune the parameters of the encoder and the decoder so that this overall energy is minimized. Okay? And we're going to put several types of modules within those encoders and decoders and obtain different unsupervised running algorithms. So there's one particular type. So principal component analysis, for example, is kind of a special case of this where you don't really have a sparsity code. A sparsity constraint, you make the code low dimensional. And you make the encoder and the decoder linear. Okay, so start with an input, run to an encoder, decode it, minimize the reconstruction error, and train the encoder and decoder so that the reconstruction error is minimized. That's principal component analysis. Restricted Boltzmann machine, which is Jeff Hinton's favorite model, is something like this also. I'm not going to go into the details of this, but just suffices to say that you can sort of view it in those terms as well. And there's a number of other algorithms like k-mean, sparse over complete basis of 4000 in field, and basis pursuit that are basically versions of this where you don't have an encoder. Okay, so these are situations where you plug an input and you run a minimization algorithm over z to figure out which value of z minimizes the reconstruction error, but no one tells you what z should be. There's no predictor that tells you what z should be. Okay? So for those of you who know what basis pursuit is, that's what it does. So basis pursuit, for example, the cost is a Euclidean distance between the reconstruction and the input vector. The decoder is a linear matrix, so you multiply the code vector by a linear matrix. And the sparsity constraint is an L1 sparsity, so it's the sum of the absolute value of all the components of the code. Okay? So basically, plug an input vector, find this guy that minimizes the reconstruction error under the constraint that it has to have lots of components that are essentially zero. Okay? And the training is you train the basis functions here so that the reconstruction is minimized. The main problem with this model is that it's not efficient if you only use it as a feature extractor because you have to run this optimization algorithm every time you get a new input. Okay? So what we're proposing is something that basically has a predictor. So the architecture of the type that I talked about before that is going to predict what the value of z is that minimizes the reconstruction error. Okay? And the good news about this is that once you've trained the system, you can basically get rid of the decoder. You just have to run the encoder, and that's a feed-forward process that can go very fast. OK. Now, here is the main idea of this talk, the main new idea in this talk, basically, which is that we're going to put some constraints on the code. And the constraints in the code are going to make sure that the energy of everything else that are not training sampled is high. And the reason why that happens is a little mysterious, but I'm going to tell you about this in a minute. Okay, so the main insight is the following. Actually, let me show you an example of this. Imagine that this code vector here is binary. It can only take 2 values. Okay, it's just 1 bit. So if it can only take 2 values, there are only 2 possible values at the output of the decoder. It's the output of the decoder when the input is 1, and the output of the decoder when the input is 0. I mean the z, when z is 1 or when z is 0, right? What does that mean? If the cost is, say, Euclidean distance, that means that only 2 values of y can have 0 reconstruction error. Okay? The only values of y that can have 0 reconstruction error are those 2 values for which the decoder, the 2 outputs of the decoder for z equals 0 and for z equals 1. Okay? For every other value, the reconstruction error would be large. Okay? So here's an example where when you make the information content of the code small, 1 bit, then the energy surface only has 2 values for where it's low, everywhere else it's high. You don't have to push up on the energy of anything. It's automatically high because the information content of the code is small. Okay? So that's kind of represented on this little drawing here. Okay? These are the 2 values of y, of the reconstruction for z equals 0 and z equals 1. And if the reconstruction error is a quadratic function, then you get an energy surface with that shape in the space of y, imagining that y is 1-dimensional, but if y is multidimensional, it's just multiple balls. So there is this sort of general idea that restricting the information content of the code alleviates the need for pushing up on the energy of everything, which is the thing that's really hard to do to solve the normalization problem. Okay? So if we have information constraints on the code, then we can happily just minimize the energy of the training samples and just rely on the fact that the code has low information content to make sure that the energy of everything else is high. And that's basically the idea that we're going to use.
So yeah, could you have a situation that you're also lowering the energy of lots of other things that you don't want to?
Okay, so the question Fernlo is asking is, do you have the situation where by accident you would also lower the energy of lots of other things without paying attention? So basically that's controlled by the sparsity, by the sparsity constraint. So if you have very highly sparse codes where the information content is very small, then there's only a few configurations that can have low energy. But if you're a little weak on that constraint, then a lot of areas can have low energy. And you run the risk of having lots of spurious low energy area, points as well. So it's how you control the sparsity constraint. And I'm going to say a few words about this in a minute. Okay, so here is the algorithm. Okay, so we have this architecture. So we tried different architectures. I'm not going to go into the details of the differences between them. There's different ways of making the code sparse. So this way that we used here in sort of our earlier papers of 2 or 3 years ago was by basically having a bunch of sigmoid functions with very, very high threshold. And so once you run the code through this, it becomes sparse just because a lot of them get clobbered to 0. And so the algorithm is as follows. You plug an x, you find a z that minimizes the sum of, in this case here, 2 energy terms, but in the general case, 3 energy terms, including the sparsity. And once you have those, you adapt the parameters of the encoder to minimize this error, adapt the parameters of the decoder to minimize that error, and you're done. Okay? Do this over training samples. So let's say you train a system like this with linear encoders and decoders and just one slab of sigmoids on handwritten digits, you get this. So these are a representation of the filters that are learned by the system, linear filters that are learned by the system to reconstruct from the code, okay? And they're parts, they're digit parts. They're like a dictionary of atoms, if you want. So essentially what this says is that because the code is sparse, what it says is that you can reconstruct any digit through a weighted sum of those basis functions of where the coefficients are almost all 0 except for a small number of them. Okay? That's the definition of parts. So for example, this 7 here can be reconstructed as a sum of 9 of those parts with sort of significant coefficients. All the other ones are essentially 0. If you train it on natural images, you get filters like this that look like edge detectors. And if you use this to train the filters of a convolutional net, so the type of network that I showed you earlier with which I did face detection and object recognition, or handwriting recognition, we actually beat the record on the handwriting recognition benchmark called MNIST with 60,000 training samples. So if we include distortion, we can get down to 0.39%, which is sort of not really significantly better than what the Microsoft guy got, like Patrice Simard, and I guess you participate in that as well? Right. So these guys got 0.4%, and we get like 0.39. It's not really significant, but it's sort of slightly better. It's very similar techniques. And the filters you get with the sort of unsupervised filter training can look really much nicer than if you purely train with a purely supervised method using backprop. The filters are not nearly as clean. Let me skip this. OK. All right, so the one method that we've developed very recently is something we call the predictable basis pursuit. So it's basically a basis pursuit where the decoder is linear, the sparsity term is L1, but the encoder is a number of different nonlinear neural nets, basically. OK? So it's basically a version of basis pursuit where instead of having to minimize the energy function with respect to the code to figure out the features, you can predict them directly from the input using the encoder. Okay? And what the system learns to produce are codes that are not only can reconstruct, but also are easily predicted by the encoder. So we use sort of various types of encoders, which I'm not going to go into the details of. We get very similar results as the previous methods, also parts when we train on MNIST. We can use those features as the input to a classifier and measure as a function. So this is to answer your question, as a measure of sparsity, what performance do we get? So let's look at this example. So here we train unsupervised, this feature extractor unsupervised with 200 features, which is fairly small. And then we take those features, feed them to a linear classifier that we train supervised with 1,000 samples from MNIST. Okay? And then we measure the test performance on the MNIST data set. And these are the two curves. So this is the error you get on the training set and the error you get on the test set. And the x-axis is basically how sparse you're making the system. So sparsity increases this way. Okay? So if the features are not sparse enough, you don't get good accuracy. If they're too sparse, you don't get good accuracy because there is not enough information in the features. And there's one sparsity level at which you get the best accuracy. So it's kind of a trade-off. And we don't know how to set it, unfortunately, other than by cross-validation, basically. So this is comparing different ways. So these are the kind of filters we get using this algorithm on natural images. And they look really beautiful. And sort of, neuroscientists tell us they look very much like filters you see in the early area of the visual cortex in the brain of mammals. And we can train lots and lots of filters to reconstruct things. So this is training 1,024 filters, 12 by 12 filters. And we get every filter does something. There's none of them dies, which is kind of cool. Let me skip this.
Don't you need lots of data to train the encoders as well?
Say again?
Don't you need lots of data to train?
You need lots of data, but it's unlabeled data. And you have as much unlabeled data as you want. Certainly here you have as much unlabeled data as you want, right? So, but even we do. So, we just steal it from you guys. So, so that's really not an issue. I mean, you can have as much unlabeled data as you. I mean, for images, it's really not an issue. So there is another variation of this that we use to learn invariant features, which I'm not going to go into the details of. Basically, it comes down to sort of separating the outputs of the encoder into two parts. One that tells you which features are present, and the other one that tells you where they are present. And I don't have to go into the details of this, but I just want to tell you that we use this to train. So basically, what you get from this are kind of movable parts now. Okay? So the filters that are learned by this thing are kind of a set of parts that you can move around. And by moving them around and combining them, you can reconstruct any say, handwritten digits. So you train the system with only a few filters, and this is how you can reconstruct this 9 as that 9 as kind of a weighted sum of those filters, and the red frame indicates the position where you have to move, place those parts. The cool thing with this is that you can train sort of a shift invariant handwriting recognizer or object recognizer with this, a vision system that includes the kind of the feature extraction layer and the subsampling layers of a convolutional net as one swoop. So we get those really beautiful filters. You can plug them into commercial nets and do object recognition with it. And on sort of standard data set like Caltech 101, we get decent results. They're not great results in terms of, they don't beat the records, but they work OK. Something like on the order of 55% correct recognition. When we did this, the state of the art was like around 60. Now actually someone came up with a method that sort of gets to the upper 70s, but we haven't worked on this since then. OK, the last thing I want to mention is a project that within which we use those ideas to, it's kind of the next project to the little robot I showed you about. We showed the little robot project to people at DARPA, and they decided to start a big project around the idea of using machine learning to drive robots around, called LAGR, which stands for Learning Applied to Ground Robots. So this project took place in the last 3 years. It ended just last month. And each team, there were 9 teams involved from different universities and companies around the US. Each team was given a couple of those robots, which consist of kind of a body with a bunch of computers inside, 2 stereo camera pairs that gives it a fairly wide viewing angle, a GPS receiver, a initial measurement unit, accelerometers and gyroscopes inside, and odometry, and a bumper. And that's all. So there's no active sensors, there's no laser rangefinders or anything. It's just cameras. Okay? So the goal is basically to use learning to sort of learn vision for robots. And the technique we used for this was, again, using convolutional nets, the same systems that we used for the demos I showed you, to identify, to basically discriminate between obstacles and traversable areas in front of the robot. But we don't want to have to kind of label every object as being traversable or not. So we designed a way to make the system essentially learn that by itself. And it's a technique that wasn't, sort of the general concept was not invented by us. It's called sort of near-to-far learning. And the basic idea is that for things that are nearby, you can get the information as to whether something is an obstacle or not from stereo vision. So by triangulation, you can figure out if something sticks out of the ground or is on the ground. Okay? And that works up to about 12 meters, 12, 15 meters or so. Past about 10 or 12 meters, you don't get enough separation between the eyes to really do a good job at figuring out what distance is something. So in that situation, you have to, far away from, in the far range, stereo does nothing to you. But at least in the near range, you can use stereo. So what we do is that we build the system in such a way that we get labels for things that are within 10 meters. And then we train online, while the robot is running, train a little classifier to discriminate between obstacles and traversable areas. And then we apply this classifier on the fly to the same frame, to the entire frame, and have it classify everything in the frame, including things that are very far away, up to about 100 meters. Okay? Now, for this to work, things that are nearby have to look the same as things that are far away. So the way we do this is basically using a trick, which is that you know pretty much where the ground is. So you can trace sort of virtual lines on the ground that correspond to a line at 10 meters and 15 meters, 20 meters, et cetera. And you can take objects that are sort of around those lines. And since you know how far objects whose foot is on that line, how far this object is, you can sort of normalize it in such a way that its size will be roughly the same number of pixels regardless of its distance. So this is what's depicted here. So you see this big rectangle here corresponds to an object that's nearby whose foot would be on the first line. Okay? And we crunch that down to, I don't know, 20 pixels high or something. And then the next line over, things would be a little smaller. Things of the same size would be a little smaller, so we crunch that down to the same number of pixels. So we get those bands, which are leveled on the horizon, where if an object appears in that band, it pretty much has the same size in terms of pixels, regardless of how far it is. Okay? Now, for the bands that are nearby, we get labels from it, up to about 10 meters, from stereo. So every window here, our stereo system tells us, I know if this is traversable or not. So we train a little classifier with this, and then we apply it to all the objects in the rest of the bands. And then we, so the features are extracted by one of those convolutional nets, which is trained with this sort of deep learning algorithm. Actually, we compared deep and just supervised, and it works pretty much the same. And And these are the results. So here is kind of a raw image. This is what stereo tells us. So stereo tells us this is traversable. This is the foot of an obstacle. And this is an obstacle sticking out of the ground. Then online, the classifier is trained for that frame. And then we apply it to the entire image. And it tells us, all the way down to like 100 meters from there, what everything is. Same above. OK, same here. So this is not based on color or anything. It's based on each decision for whether a pixel is traversable or not is based on a fairly large window around that. So it uses context and everything. It does a pretty good job. So it can detect, it can detect that there is a little passageway between those bushes all the way up at the top. That there is a corner to turn down there at the bottom. And from those, we can build maps and have the robot drive itself. So let me show you a video of this. And I'll conclude with that. OK, so this is sort of a slightly accelerated version. This is a short-range vision system, which is sort of very fast and reactive on its own thread. So you can sort of jump in front of it, and it will avoid you very quickly. The long-range vision system is actually pretty slow. It takes about 1 second to kind of process a whole frame. But it's only for things that are from 5 to 100 meters away. So it doesn't matter if it's slow. So this is the system without long-range perception. So here it runs directly towards the people, and then it needs to get about 10 meters away before it veers off. And the next sequence is with the long-range vision turned on. And here it sees from the start that there is a wall here that it has to avoid, so it sort of directly veers off to the side. That's what the system looks like from the sort of control console. And so here it's in this sort of busy footpath in a forest. And these are the, for the left and right eye pair, the labels that are produced by the sort of long-range vision system or by stereo. So stereo stops at about 12 meters. And up there is kind of the fast-reacting short-range vision system that does sort of fast obstacle avoidance. And up here is the map that's being built as the robot runs around. It's kind of a hyperbolic polar map that's centered on the robot that we built as the robot drives. And so this is so it's accelerated twice here. So the robot runs at about fast walking speed. And here it wants to go to a goal that's kind of slightly to the left of this. And it really wants to turn, but it realizes it can't go through those tall grass, so it sort of waits for the road here. Same here, the goal is kind of behind this bush about 100 meters away. And it wants to go there, but it needs to avoid all those brushes and sort of does a pretty good job, and it's basically using long-range perception for that. And the last sequence is, this is a forest path. So now the goal is about 100 meters to the left. It really, really wants to turn left. But it sees this path really far away, so it knows that it has to go straight if it wants to reach the goal. OK. With that, well, that's interesting. So I'll stop here and take questions.
This is really fascinating work. Do you
Thank
have
you.
any misgivings about what's evidently primarily a military technology?
Well, I mean, you work with whoever gives you money, right? So.
Actually, no, I don't.
Good point. No, yeah, I mean, I have some misgiving about this, but this is only, so here is where I put the limit, okay? I only put the limit on things where I can publish. So as long as I can publish the things that I work on, it's fine with me. If the things that are secret, it's sort of past the point that I actually want to work on.
In your encoder decoder framework, Is the encoder always feed forward, or during training do you have to do a search for the code to enforce the sparsity?
So during training, you have to do a search for the code. As the training kind of gets better and better, I mean, sort of as you go in training, eventually the optimal code is very, very close to the predicted code. And so once the system is trained, you don't actually have to do any minimization. You just run directly.
So the old, the autoencoders have been around for quite some time. The old ones were, will these work instead of the fancy Boltzmann machines and stuff like that? Or they have a particular problem with working here?
Well, with the kind of purely supervised approach.
Right, yes.
Well, I mean, so the only problem is that it requires lots of data. If you have lots of data, lots of labeled data, you should go for that. But in the absence of lots of labeled data, you have to use those unsupervised training. I mean, I also believe that, so there's another problem, which is that with those unsupervised pre-training techniques, we can actually train very, very deep network regardless of their structure. So even if they are completely unstructured, we can train sort of 10-layer nets. So some people at NEC, recently we heard about this at the Snowbird workshop last week, have trained deep neural nets with 15 layers, something ridiculous. Jeff Hinton also has done this. Rob Fergus also has a paper in the next, which conference is this? CPR, I believe, where he has kind of very deep architecture also to encode, to do essentially image search, image matching. So you can sort of do extract very, very compact codes for images. In this case, they're sort of fairly low resolution images, but full images. Train a very, very deep network to get to sort of something like 128-bit code. And those you can use as essentially hash codes to do a locally sensitive, semantically meaningful hash code. So you can do sort of constant time search within a huge collection of images using those compact codes. So I mean, there's huge potential for you guys using those deep learning techniques. Not just for recognition or for driving robots around, but for search, for sort of finding objects in images, for indexing YouTube, whatever. That's our next projects. If you can get money from someone else in DARPA.
Okay.
All right. Thank you.